All right, welcome back, everyone. I know we just finished a good lecture of HTML and CSS, and we're probably in our development brain thinking about how to build actual websites. But we're going to actually take a step back now and start talking about a little bit of a bigger concept of efficiency when it comes to our code, right? So the topic that we're going to be covering today has to do with a searching algorithm. Now, when I typically get a list of numbers, such as this, and let's say I'm trying to find a specific index inside of this list of numbers. Well, without knowing the value, if I had to just place in an input or create a function that would grab a value out of a list, that function would likely have to iterate through each one of these indexes over and over again, all the way until it finds the correct location. And then it could return that location out of the function, right? So that's currently what we've practiced so far. And let's take a look at what that would look like in code. Does anybody want to help me with building this searching function to return the index of an object within a list element? Let's hear it, Brandon. Yeah, you're double muted, I think.
Struggle to do this in code, so I'm just kind of speaking English about it.
Okay.
So what I want to do is I want to take half of the length of whatever I'm searching. So
Mm-hmm.
in this case, a list, I would take the length of the list divided by 2, and then I would then take that number and see if it was too high or too low in comparison to what I was looking for. So if here we're looks like we might be looking at 90. So if I said 50, it would say, okay, 50 is too low. So um, now I know that I should move to the right on the scale rather than left. So now I've just cut out 50% of all possibilities. And then I'd basically do the same exact thing and keep going in the right direction, cutting it in half each time. And then if I were to, for example, get too high, then I would just do it in the opposite direction until finally I get the answer that I'm looking for.
All right. Yeah, that was a very good way to explain binary search. But that's not currently where we're at just yet. So I'm going to go ahead and take us a step back before I finish off this drawing. So I'm going to go ahead and make a list here. So I'm going to make my list of numbers that I'm going to be iterating through. So list of numbers. This list of numbers is just going to be a list from 1 all the way up to 100. And I'm going to print my list of numbers here. Well, now if I run Python searching, we can see a clear list of numbers. All right, Len, do you want to take a stab at making this simple searching function of simple search?
Yeah. Are we talking about we're talking about linear like just a linear search, and
Yes,
then
that's
are we,
correct.
and we are assuming that I just want to make sure that I missed this if it was stated. Are we assuming the list is already sorted?
Yes, we are assuming that the list is already sorted.
Okay, I'm sorry, I just missed that at the very beginning.
Mhm.
Thank you. Um, and so are we looking for we're just looking for X, we're looking for some number?
Yes.
Okay. I mean, you would so for X in list for the number of things in the list, if X equals, oh no, sorry, because X is going to be our thing we're looking. So X, we're looking for X. So let's just say for num in list of nums.
All right, so we want ID of simple search. That's going to take in X as a parameter. And then you're saying for num in list of nums. All right.
If num equals X,
If num is equal to X.
return the I want to return and this is where I had to think about this, but so I want to just return num because that should be the that should be the value of the array index, should it not? Am I thinking of that right?
Yeah, that's so num would actually represent the number. We're starting off at 1, so it's gonna be a little bit weird.
Oh, okay, sorry, sorry,
Um,
sorry. So don't, no. So if next x equals, you're looking for x, you're going through num. If num is that, but you want to return the index, right?
right.
Because that way, if it's repeated, you're still going to get a different. You want to return the index.
Okay, awesome.
So no, I'm just think this is where I would make a print statement, to be honest with you, because I'm not there yet. Eric, I want to phone a friend.
There you
Yeah, I was
go.
gonna say, I think what you're looking for is for I comma num in enumerate list of nums. So then you have your index value to access there. If you're looking to return the index of that number.
All right, fantastic. Good. And if it goes through the entire function and it doesn't find this, it can then return -1, right?
Sure. Or I
Well,
mean, or not in list, or I mean, whatever you need.
yeah, awesome. So let's go ahead and try to make a look here at a step counter, right? Every time we iterate through this, whenever we run this evaluation, I want steps to be incremented by 1. And rather than just returning IDX, I want to return the number of steps as well. All right, let's call this function real quick. Let's print simple search. And in this case, we'll pass in 99. Well, when we pass in 99, we're going to get back that it is an index 98, but it took 99 steps to be able to find this, right? It went all the way through from left to right to be able to find that number 99. Okay, well, what if it's not within the index, right? What if what I'm looking for is something way outside the scope of what my function is looking through? Well, return -1, but took an entirety of 100 steps. Now, this isn't necessarily the behavior that I want. A simple search algorithm or a linear search, as Len referenced to it, they're both the same type of concepts. They fall within a O of N concept. We're not going to talk about big O just yet. But essentially what we're looking at is as my input size gets bigger, my number of operations that have to be executed within my algorithm to be able to find a result also grows. So as of right now, my linear search follows one straight pattern here, right? It's just saying, oh, well, as number of operations get bigger, or as input size gets bigger, so should the number of operations. All right. Now, if I were to turn this list element into an optional thing here as well. So if I were to say, hey, I want you to iterate through LST, all right? And rather than passing this into the function, what I do is I actually pass a function here that says, hey, I want you to look within a list that's within the range of 1 and 2001, the very last element. Well, when I pass this in, we can see that my input size has now grown, all right? Because my input size has now grown, so has the number of operations that it took to be able to find that element. And you'll notice that I'm utilizing the very last element over and over again. Well, when you're trying to calculate efficiency, you want the worst scenario possible to calculate the efficiency, right? In this case, since I'm just going from left to right, the worst scenario possible would be where my answer is the very last index of my list. And this is simple search in a nutshell, right? It works, it's going to do the trick, but it's not very efficient. Does anyone have any questions regarding simple search? Okay, so now let's start thinking about how do we fix that? Now, there's been a couple of different ways that I've heard this being explained, but it's essentially what Brandon brought up here, right? So we have a problem. The problem is I have to find something within the algorithm, or excuse me, I have to find an element within my list. But rather than looking through the entire list, all I really need to do is cut my list in half, right? Imagine yourself looking through a phone book. When you're looking for somebody in the phone book, you're not just flipping from left to right over and over again. Instead, you open up the phone book in the middle, you see what letter you're on, and from there you determine if that letter is after or before the correct letter that you're looking for. And then you cut the second portion in half, right? So we're going to apply the same thing to our list here. I'm going to take the left. I am going to take the right, subtract them from one another to figure out the middle, which in this case, the middle index happens to be 50. If I am looking for the number 99, if this was in a scale of 1 through 100, then what I would do is I would then cut my list in half and say, hey, I don't want to look through that anymore. Now I want to look through this second half and repeat the process. I'm going to take my left, take my right, subtract them from one another to find my middle. And this will then create 75. Then I'll do it again. I'll say, well, that's also not what I'm looking for. So I'm going to bracket one more time. Gonna take my left, take my right, find my middle, which in this case we'll have to do some sort of floor to figure this out because this wouldn't be an even number, right? So 25, that's 12.5, so likely 12. So 75 plus 12, I'm gonna go with 87. Hopefully that's right and I didn't embarrass myself. All right, so then 87 fails. We then cut this number of operations one more time. We bring it down. And now I take my left, my right, and finally in my middle, I now found my answer. All right, we can see that it's taken a considerable less time to find my actual answer. Well, this, it's almost following the same exact path, but rather than moving in this linear direction, it has a curve. Right? Where as my input size gets bigger, yes, my number of operations is going to get bigger, but it's going to happen in an exponential value rather than just a straight line. All right. So let's put that into practice now. So there we have simple search. Now let's start building our linear search function. Or excuse me, my binary search function. So I build out my binary search. It's going to take in a number and a list. I'm actually going to take this a step further here. I'm going to specify that that should be a list num, and this should be an integer. And this function is going to return an integer. All right, that's new syntax for us. That's okay. This should be easily readable. I'm specifying to myself that this number is going to be an integer, that this list is going to be a list, and that this function is going to return an integer type. This is going to help me within programming once I start writing other more complicated programs, because then when I make a reference to this binary search, you can see that it's already telling me these are the two parameters that it takes, the types that it accepts, and the values that it returns. All right. So now let's take a look at what we have here. We're going to start off just like we did with our linear search. We're specifying steps at 0. Now, just like I said inside of my drawing, I want to establish my minimum and I want to establish my largest index. How could I do that? Go for it, Erica.
By sorting the list first, so that you know which one the min and the max are.
Yeah, that's a good point. We're gonna assume that the list is already sorted, right? And I'm not looking for the min and max value. I'm looking for the min and max index. All right.
Or you want the length of the list.
Okay, yeah, that's a good try. Yeah. Brandon? Are you talking right now, Brandon? Because you're muted again if you're talking.
The list of 0 to grab the first index, and then the length of the list would be the last index.
Okay. Erica brought this up, right? Where she said the length of the list. But remember, when you're talking about the length of a list, that means you're not starting from 0, right? So if I try to do list index length of the list, that would put me outside. Eric?
Uh, could you do -1? So like list and then in brackets -1 to grab the last index.
That would give me the very last value, but what I want is the very last index. It would be like that, -1, right? So length -1. Awesome. So now my left variable is being assigned to 0. My right variable is being assigned to the length of the list -1. All right, so now I have my left and right. Now, how do I establish the middle? Brandon?
Divide the length of list -1 by 2.
All right, so let's go with middle. And you're saying to divide the length of the list -1 by 2. So we're going to go with len list -1. Okay, so this would work for the first iteration when we have 0, right? But what's going to happen when we move our left to be the middle? All right, so just like we saw in this example, 50 would now be our new left, right? And then 75 should then be our new left. All right, let's hear from Len.
Just high minus low divided by 2. You have left and right up there. I'm thinking of them as just like your higher value minus your lower value -2,
Yeah, that's close. So we're
or
gonna
left and
do,
right. I mean, I'm trying to think of which one that would be, but
yes. Uh, let's give it a
well,
chance.
it would be your left number minus your right number in parentheses -1. I mean, honestly, couldn't you just make the 0 a 1 so that you're dealing with positive numbers, because the index, you're not calling that index, you're just dealing with a number. So like length -1 divided by 2 would also give you the same answer, because it's, you're gonna start at 0, but if you make that a 1, am I making sense here?
Yeah, I get what you're saying. But this is we're messing with indexes here, which is the reason why we have numbers, right? What we're gonna do is we're gonna check the inside of the list at this current index to compare it to the number. Erica?
Oh, no, I was just gonna say, wouldn't it be left plus right divided by 2 to like make it always the left and the right? And
Perfect.
divisible by the half?
Exactly, right? So we're gonna take the left plus the right and then floor division by 2. So 0 plus 100, floor division by 2 gives me 50. 50 plus 100 gives me 150. Floor division by 2 gives me 75. 75 plus 100 gives me 175. Floor division by 2, that gives me hopefully 87. That sounds right. So I'm gonna go with that. And then finally, we would have somewhere along the lines of 98 and 100. Well, that's 198. Floor division by 2 gives me 99. Good. All right. Go ahead, Gary.
I was wondering if you could use like import math and like do median of left and right to give you the middle, or is that too much?
You likely can, right? But it may not be We'll have to talk about the efficiency when it comes to importing stuff from other packages as well, because that does get in the way of your code a little bit.
Okay.
All right. So now here's my current information. I was able to get my left, my right, and my middle. But just like we talked about it, at some point, this algorithm needs to stop searching, right? At some point, it needs to determine, hey, this number just simply isn't in here, right? Where do we think that point is? So for example, let's say we get to 99, right? And that number's still not in there. Well, then at that point, you would have 99 and 100 next to each other. They would add each other. That would give you 199. Floor division from 199 is what? Still 99, I'm pretty sure. Yep. So you would end up in some sort of loopish. So we need a stop statement. Go ahead, Brandon.
Uh, so would it be something along the lines of length of list is equal to 3 or equal or less than 3? Because if we're chopping it up into pieces, the final piece would be length of 3. So anything less than that, it no longer works.
Well, let's try it up. Let's say while len list, but we're never cutting the list, right?
Right, yeah.
So how would we say that if we're never cutting the list? Can't do it that way. What about our left and right here? Go ahead, Chris.
I was just about to ask, what's the infinity loop? Like what I don't get why we need to put a stop or whatever.
Yeah,
For
that's a great question.
Mhm.
Awesome. So here we go. What's the infinity loop, right?
You're right.
We're looking through specific subjects. We have our list from 1 to 100. Well, what's going to happen if I keep cutting them down, right? Well, 75 gets to 87. If I cut down 87 and the middle of 87 and 100, I think that's 13, so 6. So that puts me at 93, right? Then it would be 93 and 100. And then that puts me at 95 and 100. From there, it's going to put me at 97 and 100.
Mm-hmm.
And it continues on until at some point, this is going to overlap my 100, right? At some point, my left variable or what I try to assign to my left variable will either be equal to or greater than my last index or my last value within my list,
Right.
right? Once that happens, I need to ensure that I cut it. Otherwise, I'm going to get a list index out of range.
Okay. Okay, I get what you're saying now. Okay, and then all right, thank you.
Of course. Brandon?
So while middle is less than or equal to right,
Okay, while middle is less than or equal to right. Okay, then at that point, well, middle doesn't exist yet, right? I guess I could establish it in both places. Because this needs to be created within the while loop, right? Because I'm gonna reset my left and rights now. All right, so let's go with it this way. Now, how do I reset my left and right? I think you mentioned it, Brandon, right? So if my number is less than the middle, then I should be looking on the left-hand side. Where if my number is higher than the middle, then I should be looking on the right-hand side. All right, Len?
So we're trying to figure out when we need to stop, right?
I think
So
at
I'm-
this point, we're trying to figure out if we're going left or right and when we should do that.
Oh. Um. Okay, let's just the value is bigger or smaller than the number we're looking for.
Okay, so let's do that. Let's say if list middle, if it's greater than the number I'm looking for, what should it do?
Greater than your number you were looking for. It's greater than, you're gonna go right. So then your current index becomes your low or your left, and the right index remains the same.
Okay, so my list middle, right? So my 50
Is
is
bigger.
higher than the number I'm looking for. So I
Oh,
should be
Yeah,
looking
okay, yeah.
to the
Then that becomes your lower bound. That becomes your right, and you take the initial left. I would use higher and lower here. So I'm trying to my brain is trying to wrap my head around your left and right instead of high and low.
Got it. So now my right turns into my middle, right? Okay. Now let's do it else if my list middle is less than my number. What should happen then?
It should be the opposite. So then your left is going to turn to the middle.
Okay, so then my left should turn into my middle. All right, and then finally, the only other option that we have, and actually that is not correct. The first thing we should check is our target, actually. I apologize, everyone. Let me rephrase that. So first I'm going to check if my list middle is actually equal to my number. And if it is, I'm going to return the middle index along with my steps. And I should iterate my steps. Else if my list middle is greater than my number, then my left, or excuse me, my right, should now be equal to middle. And then finally, my else, which would be my left, is equal to middle. All right. So there we have our iteration process, right? Let's say in this case, the example that we have drawn here, we're looking for 99. But when I pass in my range of a list of numbers to 100 up to 99, it's going to evaluate and establish the middle. So there we have the middle at the index 49, which is the value of 50, right? From there, it's going to say, hey, is this the number we're looking for? It is not. Then it's going to say, is this current value of 50 greater than the number we're looking for? It is not. So 50 is less than 99. So it's going to say my new left, the one down below, is equal to my current middle. And that's how it attaches these two. All right. Awesome. Well, let's take a look at what's going on here. I'm going to go ahead and print steps. I'm going to print middle. And let's see what we get. Again, 99. And then we're working with a range of 1 to 100. And rather than working with simple search, we want to work with our binary search. Let me run it real quick, Brandon, and then after that, we'll address questions. All right, so we just ran it, right? It's returning my steps and the middle. Oh, excuse me. It's returning them backwards. So here's my return. It returns the middle, which is the index. So it's saying at index 98, we were able to find the value that you were looking for, and it took us 7 steps to find it. So that's a lot faster than taking 99 steps to be able to find it. All right. Brandon, go ahead.
I was just gonna request that we had both print statements on there just to see, but you took care of it, so.
Oh, awesome. Erica?
Wasn't the search for 99?
Yes, the search is for 99. That's why it's located at index 98. Remember, we start counting from 0.
Oh yeah, I see index. Sorry.
Of course. Any other questions? Okay, awesome. So now we've taken a look at our number. Typically you don't want to compare your middle and right. Instead, what you actually want to compare is your left and right. All right, so I'm going to compare my left and right to ensure that they're less than or equal to. The algorithm still works. I don't have any unexpected behavior. Good. So now it's working correctly. Let's say we're looking for the very first middle index, right? What happens when I'm looking for 50? Well, when I'm looking for 50, I'm getting, hey, we found that at index 49 within the very first step. Cool. Well, what if I'm looking at the start? What if I want to find the number 2? Well, we were able to find it in 6 steps, and it is at index 1. Great. So it kind of works a little bit counterproductive in that sense, where if I were to do a simple search, I would have found it within 2 steps, right? But think about the maintainability of it, right? Even at the very last or second to last index, my number of steps never rose above 7. So this is a fantastic way to actually look for said algorithm. Now, we've applied this so far utilizing numbers, which sure, it works as of right now, but it's not necessarily just applicable to numbers. Let's take a look at what it looks like when you apply it to a list of names. Right, so let's say list of names, and let's make that equal to, let's see, Francisco, Adam, Momo, who else do we have? We have Len, we have Erica, Polly, and now I have to include both Brandons, because I can't just include one. All right. Let's see, who else do we have? We have Eric. All right. Considerable amount of people. All right, I have my list of names. Well, can I apply this algorithm now? Let's see.
Sorted.
Yes, let's take a look at what it looks like, right? So I'm gonna apply both of them. I'm gonna say simple search. I want to find, and I should probably make these unique. So I'm gonna put Brandon Y in there. So I want to find Brandon Y within this algorithm. And the list that I want to pass in is my list of name. All right. Well, now let's also print our binary search. And again, I'm going to look for Brandon Y. I'm going to pass in my list of names. Well, now when I execute this code, we can see one of them worked, but the other one seems to be stuck in some sort of infinite loop. Go ahead, Erica.
We gotta sort it.
Yeah, awesome. So what's actually happening here is my algorithm has no idea how to figure this out, right? It doesn't know how to iterate through this information when it's not a sorted algorithm. It's not being sorted for me. So how do I fix that? Well, we did it with numbers when everything was from 0 to 100 and everything was sorted. The same thing applies to names. All right, I could go ahead and say list of names dot sort. And now if we print list of names, I believe list of names is destructive, meaning it alters the original data structure. So if we take a look, now we have it completely sorted, right? The original data structure has been sorted. Oh, go ahead, Eric.
I was curious, like what the trade-off is in using sort, because I believe it uses bubble sort, which is O of n squared, which I don't know if that's even like less efficient to offset the benefits of binary search. I feel like the only times I've seen binary search make sense, at least in like challenges I've been given, is when it's already sorted for you. So you have to like just happen across a list that's sorted really, instead of doing it yourself.
Yeah, that's a great question. We're going to be covering sorting algorithms later on, and they're going to kind of tie to each other, right? But yes, simple search, or excuse me, binary search should definitely be prioritized or used. The juice is only worth the squeeze when you're being handed an already sorted list. Does that answer your question, Eric?
Yep, thanks.
Of course. All right. So now when I run this searching algorithm, we can see that my simple search was able to find it within 3 steps, and my binary search was able to find the same thing within 2 steps. Very closely related, but I can see the efficiency, and I can see that it not only applies to numbers, it also applies to strings. The thing that we need to ensure always gets passed into this list is that we have a sorted list. Otherwise, this algorithm will not work. All right. Let's do a quick review here over our simple search, or excuse me, over our binary search. That's not it. All right. So we're going to take a look at the code at the same time we're doing this. And yes, I just took off a line of unnecessary code. If I run this again, it's still going to work perfectly fine. So there's my steps, my left and right. All right, so first I identify my left as 0 because every index or every list starts at 0. So I know that my very bottom index will be 0. I don't need to worry about that. Then I take the length of my list and subtract it by 1. So len, list, minus 1. Which in this case is going to be equal to 99. And actually I made a mistake here. I've been referencing the value rather than the index. So this would tell me that my middle is 49, right? So there you go. I was able to find my left index, my right index, and the middle. Good. So it goes into my algorithm. I've made a step. Determined my middle was 49. What it says, hey, is this list middle? What's inside of this? What I'm looking for? Well, what's inside is the value of 50. The number that I'm looking for is 99. So no, it doesn't match. All right, moves on to my next statement. Well, is it greater than 99? It isn't. So it says, fine, if it isn't, then we're going to set our left index to middle. So then it makes a copy. And we drop it down for our next iteration. So now our left is 99. Oh, excuse me, our left is 49. Our right is still 99. And we have to find the middle between those, right? So it adds them together. 49 plus 99, that's 148. And then it does floor division by 2, right? So that's going to be 79. So then it goes over, marks index 79 here. Then it says, well, what's inside of this value? Well, inside of this value, what we have is 75. Or excuse me, actually it would be 78 in this case. All right. So then it goes through the statement all over again, takes another step, and it wonders, all right, well, is this equal to the current number that I'm looking for? It is not. All right, well, is this greater than the number I'm looking for? It is not. Then in that case, let's set the left to 79. And it drops it again. And it continues this process over and over again for 7 steps until it's able to find 99. All right, so that's the benefit of our binary search, whereas our simple search or linear search, as otherwise referenced, would quite literally take 99 steps every single time to be able to find that last index. Does anyone have any questions regarding binary search versus simple search? Go for it, Erica.
Don't want to be like, but 49 plus 99 is 148, right?
Uh-huh.
Divided by 2, that's 74.
74. There it is. Thank you. Appreciate it. That quick math. And that's why that puts me at 75. Look at that. It's almost like it makes sense. Thank you. All right. Okay. If there aren't any other questions, before we kick off for the rest of the day, I did promise everyone seeing a full stat. Oh, we do have a question. Go ahead, Len.
I have a question for you.
Yes, sir.
And I already know the answer, but this is the thing that made sense to me when I first learned this.
Uh-huh.
If I double size the list, how many more searches will I go for? If I go to like 200 items, how many searches will it take?
Yeah, let's check it out.
I'm just wondering what you think. I mean, this is an interesting one for me.
It's not going to take double. So if I were to turn it into 2,000 items, rather than taking 7 steps, it would probably take about 10 steps.
8. Every time you double information, you only add one more step. And that's one of the things that makes this such a powerful search algorithm. But you said it earlier, only when the data is pre-sorted. So like that, this is that as we go through the algorithms thing, Francis is going to talk about, there are certain things you got to think about. Sorted, not sorted, and then how fast is it growing? You talked about both of them already. And it's just interesting that double the information, only go up one more step.
There you go. So we could see it here, right? If I were doubling the information, we would only go up a very small amount of operations. I think this visualizes it pretty well. All right. Yeah, that's great. Thank you so much for pointing that out, Lynn. Let's actually see it in practical application real quick. So we have our binary search. I'm actually gonna copy that. All right. And what I'm looking for here is going to be a number and list of range. All right, so in this case, I'm looking for 99. In this case, I'm looking for 199. And one of them, I'm going over to 101. And in the other, I'm going over to 201. So I'm doubling the input size. Let's take a look here. All right, so there you go. You have 98 for 7 steps, and you see 198 for only 8 steps. Awesome. Thank you so much, Len.
Yeah, if you double it again, it'd be like 9, right? So with the 400 to be 9. You can just keep doubling it and it'll always just go up by 1. That's the cool thing about this one. But it's got to be pre-sorted.
All right. Are we assuming the list starts out ordered? Oh, yeah, thank you. Sorry, I'm a little late to the party there. I apologize. All right. Well, it's going to conclude our lecture here. So I'm going to go ahead and stop the recording for this one. Oh.